So we're going to start chapter 2. Chapter 2 is really definition. One thing I really like this handbook is it repeats the phrases, important phenomena, phrases, definitions. The authors are repeating in chapter 1 a little bit, chapter 2. When you go down to chapter 5, it repeats also. For example, it shows here lots of the parameters, shock wave, or deflagration, detonation, blast wave. It repeats also. So that repeating is the way I really always use it as a teaching tool, because if you hear once, it doesn't stay a long time. The second time, when you hear, it doesn't stay a long time. About 3 or 4 times when you listen, then it stays. It just engraved in your brain, so it will stay for a long time. So that's what's happening. So here, the definition-wise, I'm gonna really read it through. Then I want you to feel it. The explosion. When you hear the explosion, we're going to repeat same thing later. When you hear the explosion, what clicks in your mind? We've got to talk freely. When you hear the explosion, it doesn't matter whether it's a gas explosion or conventional chemical explosion. What clicks in your heart? Any comment? You decided not to talk? I better go home. That click is important. When you hear the 봉식, well, you are sitting right here, so when you hear the explosion, what clicks in your heart? Bomb. How about Yongyan? 급속도로 진행되는 거. 성태는 뭐가 생각이 나? 경석이는 reliability. What clicks your mind? Explosion. 예술이는 뭐가 생각나? 크게. It's all same. It's, you're talking a little bit of the whole concept of explosion. Rapid change in pressure. That's what I want you to remember. Explosion, not slow change in pressure. Extremely fast change in pressure. So explosion generate the shock wave front, right? Shock wave, right? Then it has a discontinuous wave front. So, whatever you say is all correct. There's no such a thing as wrong thing, no. But explosion, we're going to review down here quickly also. Combustion. When you hear the combustion, what do you have in mind in Korean or English? Combustion. Burning. That's what the combustion is. It's nothing but burning, right? Simply speaking, gas explosion. Gas explosion, people uses all different kind of the names. Vapor cloud explosion, different name. It's all same. it described in chapter 2. So, and confined gas explosion. When you really confined the environment, then the power it generates is tremendous. If it's unconfined situation, then it's not important. But Dr. Kim, he visited the Busan University the day before yesterday. They are building the AirX explosion chamber, air explosion chamber, and also underwater explosion chamber. And they are building explosion facility, spending about 600 which means $60 million. It's amazing how they really got that such a large sum. And he just bluntly told me the pressure they are designing, max pressure is about 20 bar, 8 bar, about 5 bars. So when I hear 5 bars, it clicks something in my mind. What does it click your mind? When you hear 5 bar as a maximum pressure, what do you feel about it? That's not for conventional explosion chamber, but that's for what explosion? Gas explosion. Gas explosion doesn't go up that high, but 5 bar seems to be, I feel, low. But they could say the limit of amount of the fuel to explode. But I would go at least 10 bars. But that's what happened. So unconfined gas explosion, vapor cloud explosion. What does it talking about? Same as gas explosion. We're gonna try to talk or just to concentrate on gas explosion, but it's all same. Cloud, vapor cloud explosion, same as gas explosions, okay? And the flame speed and the burning velocity, we're gonna spend the time a little bit. The burning rate, when you talk about the burning rate, you're talking about the burning rate of the fuel or fuel-air mixture. So then you're talking about the mass per unit time, which means a kilogram per unit time. Now deflagration coming back, detonations coming back, turbulence and hydrodynamic instability, it covers very simple, half a page or 1 page, so you know better than showing here. And the flash fires. When you hear about the flash fires, what do you have in mind? You should feel no pressure. Flash means right on the street. There is a fuel running and fires on there, and there is no pressure. Pressure is really absolutely minimum. And blavis. When you hear about the blavis, what do you have in mind? I'm not trying to give you a harder time. You want to communicate together. So I want you to smile. So Sangtae is always smiling. That's good. Abdullah, you're late, but smile, okay? So blavis is mixture is boiling, right? Boiling, high temperature, and confined in the pressure vessel. Then explosion occurs. It's detrimental. That's what the blevis is, right? I don't have any right now. It's a practical field experience. I don't. But conventional explosion, of course, I have lots of field experience. I can tell much, but gas explosion, you are better than I do. Okay, so then shock wave, we are talking again. Blast wave. Blast wave, what's uniqueness in the blast wave? When you hear about the blast wave, it doesn't click anything. 정호? Say air. It happened in air. Yeah. Explosion occurs in air. Then of course it generates a wave. It's called the blast wave. When you hear about the blast wave, explosion occurs in the air. Okay. That's what the uniqueness of this is. The pressure, we're going to talk about all this. So I put the red mark right there. The vapor cloud explosion, fuel air explosion, unconfined, whatever all this is all called the gas explosion. So don't confuse. When you read a textbook, they're using all different kind of the names. So again, this was in chapter 1, and the rapid increase of the pressure. That's what the explosion is. Combustion and burning of gas, liquid or solid, where the fuel is oxidized, involve heat release and often the light emissions. Emission is something like a byproduct. 이렇게 찌꺼기 남겨지는 거. 그리고 여기서는 light emission 하면 이렇게 조금 이렇게 찌꺼기가 남는 거 이렇게 생각하면 돼요. Then you saw this equation I saw when Professor Han talked about the fire. And as a byproduct, there's energy there. So if there is no energy, the methane plus this is just air. As a result of explosion or process, it generates CO2 plus water plus this is air product. If there is no energy, what do you call this? You have a process called? I learned from the fire. I think it's coming down here. If it's not, I'll wait. It's not showing here, so let's wait for a few minutes. And I didn't highlight all this, which means you can just read it through. But whenever I feel the discussion item, I put bold word or things like that. Combustions of gaseous fuel in air can occur in two different modes. One is fire, which is fuel and oxygen is mixed during the combustion process. Another one is fuel and air, but I don't know what's really big. big things about it. But air, fuel mixture, oxygen and fuel mixture. But as a part of the air, of course, there's oxygen involved, and air contains a lot more. And as a result of mixture, explosion of the mixture, when it explodes, it shows what happened. Same thing here. So repeat, gas explosion is talking about it. And confined gas explosion, confined gas explosions are the explosion within the tank. When it shows within the tank, then that's an internal explosion. It's no longer external. Internal explosion generate a lot higher detrimental result. So this is like a pressure vessel here. So when you have a burned gas and it could explode, it's not going to explode in any temperature. So depend on the type of the fuel or a mixture, the bound of the temperature are all different. So hydrogen looks like in the wide range of the temperature, it can ignite almost any temperature. So it looks very dangerous. So this is burning gas chambers, fuel air or fuel. It's a partly confined explosion. A lot of situation you have, you will face partly confined explosion environment, and this is what it shows. And this items is obstacle. Whatever they generate the blockage in the room or confined area. But in this particular drawing, it really shows the vent opening as a one, but does not have to be one large opening. It could generate small openings all the way around. As you see all different types of the opening, then pressure reduction is severely affected. And when you conduct testing next year for containment explosion, we're gonna use such the configuration in the bag. About 1/3 of the bag is open. Let the pressure is just relieved through that opening. But this obstacle, they call this stuff is as obstacle. This reduced the pressure also quite well. So in their design, they are installing, and another situation is, of course, inside the space, then they have a lot of equipments which have to be installed in there. So that will reduce the pressure significantly. Unconfined explosion, you can really see here. But in offshore, I don't know whether you visit the drilling platforms and all that. Anybody really visit offshore structure? You did? How was it? Is it big, huge? Hmm? How big?
Hard to look around all of the stuff because it's too big.
So is it like something like 100 meters diameter.
I have no idea about the size of it, but
It's all the piping systems all there. Then this is like for the unconfined situation, unconfined explosion. When gas explodes in such an unconfined area, it could severely affect the whole system. The largest open field in the ocean I had is aircraft carrier. Aircraft carrier, I was in there for a week. It's a huge. In the morning, all the soldiers, they all come out there and do the jogging all the way around, and so big. It's amazingly big. Of course, they have a fire once in a while because in the training mission, they have to practice the jet coming down and try to land using by one blue light in the carrier runway. And we all stand in the bridge. Then we were watching. Some couldn't make it. Some pilot, I think he was so scared. It's something like a couple 100 miles away from San Diego that night. It was really dark. You can't see anything except the one blue light at the middle of the aircraft carrier, the runway. Then one tried 3 times, couldn't touch down, couldn't get the hook to the cable. In there, they have a cable. Then at the back of the aircraft, it has a hook. So they have to catch the cable. They couldn't do. And sometimes it crashes right onto the runway and have a fire, but when they have a fire, the team is ready to remove right away. So it was very interesting experience I had. And platform, as Yesu mentioned, is huge. And when you get the fire, they have like unconfined environment. Then the fuel-air mixture spread all over. So, but again, the pressure level is low for the unconfined. If it's confined, of course, pressure level rises up. So read through. Over here, if you look at here, if the unconfined cloud, this is really unconfined cloud, gas explosion in unconfined area. You're talking about in the order of the 20 bar G. Last week I mentioned about the bar G. It appears. What's the bar G? This bar G, I mentioned to absolute pressure, but it's not the absolute pressure. Correction. The bar G is equal to gauge pressure, gauge bar. Okay, it's a gauge. Gauge bar is the pressure measured by the gauge. So then, of course, it shows up. So right on the ground, if you measure, then it will generate, it could generate absolute pressure, something like 14.7 psi, or 100 K pascal. Okay, it's absolute. Then you reset that gauge to 0. Then from that point, whatever the dynamic pressure you measure as a result of gas explosion, for example, it just register this the G, bar G, gauge pressure, okay? So gauge pressure is relative, not the absolute. So this is relative. This is relative pressure. Don't confuse. And another one is a bar A. A means is absolute pressure. So if I just draw the P versus T here, if I just write the pressure variation, shock pressure, so this is a 0, then if you measure up to here, from here to here, that's absolute pressure. I could say the bar A. And if you say from here to here, then that's bar G, gauge pressure, because it reset to 0. That's why when you conduct any explosion testing, that's what I always said. You know, we put the gauge in the reservoir, 저수지 out there. We put the pressure gauge 10 meters or 5 meters, reset the gauge to 0. Yonghyun, you did, right? Always set to 0. Then whatever the measure is a dynamic pressure, which is a gauge pressure. So this is equal to the dynamic pressure. Okay. I think I first lecture, when I face bar G, I say, oh, this is absolute. Where I take a look at, where I go find out? Internet. You go internet, type in bar G, you type in bar A, all the things are showing out there. That's a fantastic, isn't it? So 20 bar G, in order of 20 bar. 20 bar, but Busan University setting up the chamber for 5 bar G, which means a small experiment they can conduct, not a large experiment. In the platform, when they design the piping systems and all that, they could use more than 20 bar G, could be higher. So when you have a bar G value, and when you're dealing with what would be the absolute pressure right on site here, all you have to do is bar G value plus 1 bar, because this atmospheric pressure is 1 bar. Then that's absolute, nothing big. Have you seen the VCE? Yes, vapor cloud explosion, same as gas explosion. This flame speed and the burning velocity, I want you to pay attention on the definition portion. This is similar to when you take a dynamics course, you learn about the relative velocity. Okay, aircraft is moving in that direction, another aircraft is moving in that direction. What's the velocity that one aircraft feels when he look at the other aircraft. Not the absolute fixed, not the velocity relative to any fixed point on the ground between the two up in the air. Two aircraft, one moving in that direction with a particular velocity, another aircraft moving in that direction with another particular velocity. The pilot sitting here is look at this, okay? Look at this, then as he look at it, this plane move pretty slow. That's relative velocity. As the two planes fly parallel, and if they fly parallel with the same speed, as they look at each other, then looks like they are moving with a zero speed, right? That's relative velocity. So here is exactly same concept. Flame speed, when you say about the flame speed, that's the absolute velocity with respect to the fixed point. So when you see the flame by the mixture, air-fuel mixture, right? And of course there is always a flow of the unburned gas, unburned fuel. Fuel is moving. So if you look at the relative velocity of the burned fuel or flame with respect to the unburned gas, then that's relative speed. So that you have to be kind of careful. So flame speed is S, is defined as a velocity of a frame relative to a stationary observer, or that is the ground or any fixed frame, right? So this is absolute frame. When you say flame speed, that's absolute velocity. This aircraft flying this direction, then absolute, this velocity of the plane is with respect to or relative to the fixed point on the ground, then that's flame speed. The burning velocity, U is the velocity of the flame, not frame, flame front with respect to the unburned gas immediately ahead of the flame. One time I gave a thought, why does it say ahead of the flame? The unburned gas is running, that's what I visualize it. Then flame start really behind it. So unburned gas is always flowing ahead. That's what I visualize it. Then relation is the flame speed or velocity is equal to the U is a burning velocity, which is a relative velocity. This is absolute velocity plus small u is velocity of unburned the gas, unburned the fuel. And they have there's a one-dimensional, just a picture, and this is flame speed. This is unburned gas. So this is a u, small u. Okay, so the burned gas has, of course, a speed itself. So S is equal to U, capital U, plus U. But it's a vector, the velocity is a vector, so direction matters. But pressure is a scalar quantity, so direction doesn't matter. Right, so that's one. So a lot of things, so when you read, you can learn. It's good. The burning rate is, as shown here, is a kilogram per second. That's all I can mention. The rest you can read. Burning rate. And deflagration, whole chapter 5 is about the deflagration. So that doesn't mean that I'm not going to say any word here, no. Deflagration, repeat the same thing. We have learned a little bit in chapter 1. In chapter 2 is a definition chapter. Deflagration is simply speaking, by saying one word, deflagration is what? Rapid burning. It's a burning. Detonation, rapid burning. But speed is different. Deflagration is much slower speed. Detonation is a higher speed. That's what you should distinguish. When you say deflagration, you're not talking about the really shock wave. When you talk about the detonation, then you talk about the shock wave. It generates the discontinuous the wave front. So that's what the detonations, the wave it generates. So deflagration, burning rapidly. What speed? Julie, what speed? Say subsonic speed. Subsonic speed is speed less than acoustic velocity for that material, unburned fuel, for example. And detonation, which is higher velocity, which is higher than the acoustic velocity. So again, if this is like a chemical explosion, I can tell clearly, day and night, clearly about that. But here, gas explosion, you can't tell. You can't tell. Because depend on the type of the fuel. Acoustic velocity in the fuel would be different. So acoustic velocity of oil and water is different. Acoustic velocity along the aluminum would be different from acoustic velocity along the steel. But as a family is closer. So that you have to consider. So rather than just using the common, don't just use a common sense for gas explosion. You've got to build up the experience yourself. I could tell a lot of common sense in chemical explosion problem, but gas explosion problem, you can't tell. You can't just use a common sense. Trend you can tell, but not exact. So in that sense, you really have to study the case by case. In this handbook, they shows quite a few different cases, which means different experiment. That experiment, you can learn the trend, but not absolute. So deflagrations, I think we talk enough, but again, deflagration speed is 1 meter per second, up to 500 to 1,000 meters per second. Gosh, that's a stupid range, isn't it? 1 meter per second to 1,000 meter per second. Authors are not stupid. You know, that's what they face for the gas explosion. Chemical explosion, we never say that. We say 1,500 meter per second, plus minus a little bit, depend on the temperature and depth of the water. That's it. But not like this. From 1 meter per second to 1,000 meter per second. That's what the nature problem for gas explosion. Understandable? You have to accept it. That's what the differences are. And the pressure is pressure, explosion pressure is between, this m bar is a millibar to several bars, millibar to several bars, quite a bit. But again, deflagration, the pressure level is really low for the rapid burning situations, not the detonation. Detonation is now coming here. So detonation, as we understood, speed is supersonic. You can tell. Larger than speed of the sound in that unburned gas. Okay. This gender theory, I look at the internet to really see J&D theory. This is the initial of the author's name, but I don't feel we don't have to go down to that depth to study type of the flame based on such a theory. You don't have too much worry about that. Burned gas reaction zone. This is for detonation, the wave. Right at here, this is a simply tube type. But if it's detonation wave generate, it's going to be a really spherical. Okay, so behind the shock wave, of course, it generates the burned gas is there. It's a mixture. And this reaction zone is interesting. And the unburned gas is in front of the shock wave. Here is no shock wave was there. So reaction zone, this thickness, they never talk about it here. This thickness, I'm pretty sure in the gas explosion is thin. When I say thin, it's not paper thin, but some thickness you might have to consider. And this reaction zone, what happened here is right at the shock wave, front of the shock wave, a rarefaction wave or reflection wave could happen. So this is a quite complex zone here. For chemical explosion situation, we can consider the shock wave front as a paper thin. For the nuclear explosion, it's very thick. So when shock wave, nuclear shock wave passing by in the water, the whole submarine can trap right in this zone. Shock wave front, then it kills everything. Vice versa. So this is very complex zone. Here they call the reaction zone. here. Okay. It shows here for fuel layer mixture, blah blah, it's up to 2,000 meter per second, and maximum pressure produced about close to 20 bars. Turbulence is turbulence. You know better than I know. Laminar flow and turbulent flow depend on the range of the Reynolds numbers. You can designate below that Reynolds number, you can say laminar flow. Same thing applies to this gas explosion problem. And definition of the Reynolds numbers, you know. And this is what the cylinder in a cross flow situation. And hydrodynamic instability is concerned. This is called based on the Taylor instability. Anybody learned about the Taylor instability? I think some of you took the hydrodynamic course. Higyu, you took the hydrodynamic course? No? Anybody heard about it? So where to find it? I access to internet, then type in type in the Taylor instability. It shows a long story about it, but again, some simple theory which is not good enough, but I want you to read for that. Flash fires, I mentioned about that. The unobstructed gas cloud produced negligible overpressure. So pressure you can neglect. Blab is, we talk about it. And blab is, yeah. So good material to read. Shock wave. Shock wave, one thing you could remind yourself is shock wave in a gas can be defined as a fully developed compression wave, not the tension wave, not the rarefaction wave. It's a compression wave of large amplitude across which density, not just the pressure, density, pressure, particle velocity change drastically. That you have to, so it's a shock wave mentioned. Blast wave is air wave in the motion by the gas explosion. It's okay, blast wave. Air racks, they are dealing about the blast wave. Tunnel design for defense purposes, we have to consider the blast wave. Okay. So all this blast wave and the pressure, we talk enough already. This is the last section. And the pressure, there is one additional thing so we can talk, understand this, I'll finish in a minute. Dynamic pressure, okay? And also static pressure. And the total pressure is, of course, summation, sum of static and dynamic pressure, but it could generate stagnant pressure. For example, at the tip of the sphere, when the the flowing flow comes right here, when it hit it at the vertex point, then velocity is equal to 0, but pressure is not equal to 0 at that point. Then you can say that that's a stagnant point. then stagnant point it generates the stagnant pressure, which is a summation of both the static and dynamic pressure. That's what this particular section is talking about. Okay. Okay, I'll stop right here. And chapter 3, I'm going to spend 10 minutes on Monday because number of pages small, but some experimental result they conducted, I want you to read. So Monday, before you come into class, read chapter 3 and chapter 4, would you? So we're going to do Monday in chapter 3 and chapter 4.